My name is Vihan. I work with machine learning research team at Google. And today I'm here to introduce you to the different machine learning tools that Google has built and open sourced over the past few years. My aim for this talk is to describe different ways you can get started with these tools. And hopefully by the end of this talk, I'll leave you with enough pointers that you'll be able to use one of these tools to apply machine learning to different problems that you see in your personal and professional life. So before we get started, let's look at machine learning in action around you today. Google Play Music. We use machine learning to model users' interaction with different artists, different songs, different music labels, to recommend them good songs at any point during the day. Gmail. There's actually a lot more spam than actual mail in the real world, and hopefully you don't see most of it in your inbox. This is all thanks to really strong classifiers that we have built using machine learning that are able to filter out spam from non-spam emails. Google Photos. This is personally my favorite. And if you use Google Photos, you probably have seen this in action. But as soon as you click a photo and you upload it on cloud, the image recognition model kicks in, and it's able to detect various objects in your images, and you can search them using text. So for example, I went to horse riding with a couple of my friends a couple of weeks ago, and then yesterday I was showing it to my friend, and all I had to do was just photos of me riding a horse. That's it. Speech recognition. Again, an area where we have made huge progress over the recent years, all thanks to deep learning. This is evident from the fact that people are talking more and more to their phones than typing. This is really, really exciting. Smart reply in Inbox by Gmail. So if you use Inbox, you might have seen that very recently we started showing these nifty suggestions. And these are based on the content of your email. And as per a statistic, 10% of all responses sent on mobile use these suggestions. It's a really significant traffic. Google's DeepMind AlphaGo. It recently shocked the world by defeating the world's Go champion. And in AlphaGo, we actually took a step further, because here the machine learning program, it not only learned by looking at how humans play Go, it not only learned just by playing against humans, it actually learned by playing against itself. Self-driving car. It's really hard to imagine self-driving car without machine learning. A lot of really complex problems, like detecting pedestrians on the road, detecting hand signals of cyclists, they all become really easy to solve using machine learning and computer vision. So now that we have seen that machine learning is all around you and Google is really betting big on machine learning, but our mission at Google is really to empower the developers with really great machine learning tools that they can use to apply machine learning. And as a developer, there are broadly three ways to get started with machine learning. The first way, it's just to use off-the-shelf, ready-made, cloud-based API or mobile APIs. You really don't have to understand any logic. These are really simple to use, intuitive APIs. The second way is to use an existing model architecture and retrain or fine-tune on your data set. This is a really simple but very powerful technique that research scientists in academia and now engineers in the industry are now using to develop really, really powerful models without having to start from scratch. And we'll see a demo of this during our session today. And the third technique is obviously, it's the most flexible, but probably requires slightly more knowledge of machine learning, is to develop your own machine learning models for new problems. So let's see how you can get started using cloud-based or mobile API. I'm not going to go too much into details because Yufeng, who was the first speaker today, already covered these in detail. So just a quick recap, Cloud Vision, it's the API that detects objects in your images. So just upload an image and it will detect objects, it will detect text. Cloud Natural Language, this is given text, it recognizes structure in your text, it recognizes the sentiment of your text, cloud speech to convert your speech into text, and finally cloud translate, which is to translate from one language to another. And this is the, if you haven't tried these APIs yet, I would really recommend you going to cloud.google.com, products machine learning. You can see all of them in action. It's free. It's really cool to see how powerful these APIs are. So let's really get started with the second technique, which is to use an existing model architecture and retraining on your own data set. But before we dive any deeper, let me quickly introduce you to TensorFlow, which is Google's machine learning library that we open sourced around a year ago. And TensorFlow, it's really fast, it's really flexible, it's really scalable library for machine learning. And you'll see in a second why I'm using all these adjectives for it. It's already being used by research scientists in different universities. It's the default way of doing machine learning at Google. A lot of other companies are also adopting TensorFlow because all of it is open source, and we have some great tutorials that help you get started with it. So the name TensorFlow, it's actually composed of two words, tensor and flow. So what is a tensor? Tensor is a multidimensional array. It could be an array of integers. It could be an array of floats, strings, whatnot. By multidimensional, I mean it could be a scalar, like 7 apple. These are all tensors. It could be a 1D array. It could be a 2D matrix, a 3D cube, anything. And flow is how these tensors flow through the graph of operations. So in TensorFlow, you define your computations in the form of a directed acyclic graph. The nodes in the graph represent the computations, and edges represent how the data or tensors flow through these computations. So as you can see in the figure on this slide, all the nodes, they represent one operation or the other, like addition, multiplication, and so on. And the edges represent how the data or tensors are flowing through these operations. So to code in TensorFlow, all you have to do is you have to define a graph, and to do that, you can use one of the front-end languages. The most popular is Python. And once you have written your graph, it's compiled and optimized. And once you have a compiled graph, you can pretty much deploy it on any available local, low-level device. Like you can run the same code on GPU, on CPUs. You don't have to do any special. You don't have to write any custom code to make it run on a different platform. It just works out of the box for you. And so at a very low level, TensorFlow is actually just a library for numerical computation. So if you can represent your, computation as a graph, you can use TensorFlow. And in fact, if you go to tensorflow.org and you see the tutorials there are actually a lot of tutorials which have nothing to do with machine learning. But TensorFlow, although it's a library for numerical computation, it's specialized for machine learning in the way that it computes gradients automatically for you. So gradient descent is a really popular algorithm for learning in machine learning. And since computing gradients is such an important operation or such an important computation in machine learning, TensorFlow does that out of the box for you. So you don't have to write any special operations for computing gradients. It just does it automatically for you. So the core of the TensorFlow, it's written in C++ for performance reasons. And as I said, you can interface with it using different front ends. Python is the most popular. We also have a C++ front end. And the developer community is adding many more. And all the code is on GitHub. Once you have a compiled code, as I said, you can run it on CPU, GPU, TPU. You can run the same code on mobile devices like Android, iOS. You actually don't have to do any special custom logic for running it on different environments. And it's really portable in the fact, as I said, you can take the same code. You can run it on a laptop. You can run it on data center. You can run it on mobile devices. It's really scalable. So the TensorFlow code is really optimized at very low level. So it just uses all the available resources to it. So let's say if you run the same code on 100 machines, so ignoring all the network overhead, the code that runs on 100 machines would be roughly 100 times as faster as you run it on like a single machine. So it's really scalable. It scales really well to production problems. So now let's see how you can use an existing model architecture and retrain it on fine-tune on your data set. So image classification, it's another domain where we have made a lot of progress because of the advances in machine learning. So Inception is the model, that was, there has been a lot of research on these models. So Google actually came up with a really, really advanced model. It's called Inception v3, and this is the architecture of this model. You can see that there are so many layers stacked on top of each other. This model was trained on ImageNet data set. It's an open source data set containing millions of images, and it was trained to recognize 1,000 different categories of objects. Like, it is able to recognize different breeds of dogs, different breeds of cats, electronic appliances, and so on. So it's a really powerful model for image recognition, and the performance of this model is actually pretty close to the human performance. But let's say you want to train your own image classifier, and you have some data. So let's say I want to train an image classifier that will classify different kinds of flowers. So let's say I have a training data set that contains sunflowers, roses, and tulips, and I want to train an image classifier that is able to differentiate between these three kinds of flowers. So one way is obviously to start from scratch. I can create my own Inception model, much similar to the figure in the last slide, and I can train it. But the complexity here is, since it's such a complex model, it will take multiple hours or maybe even multiple days to train this model. So another strategy that people have started doing very recently effectively is start with the base model, say Inception, and then retrain only a certain portion of this model and retrain using your own data set. And the reason it works is because the Inception model, it's already very good at detecting very low-level attributes in our images. For example, detecting lines, detecting corners, or even high-level attributes. Like, it's also able to detect some high-level attributes like eyes or petals of a flower and so on. So since it's already good at doing these things, and the image classifier that we want to build is also, it also needs to know all of these things. There's no point in retraining from scratch. What you could do is, you can just take the same model and retrain only a certain portion of it using your own data set. And it's a really simple process. The demo that I'm going to show today, it's a really simple two-step process. All you have to do is first collect your training data. So in this case, I'm trying to build a classifier that is able to differentiate between sunflower, rose, and tulips. So I have images of sunflowers, roses, and tulips all organized in different subfolders. And then all I have to do is just use the open source TensorFlow code and just point it to my training data and specify how many training steps I need to run it for. And without writing any line of code, I'll have a really powerful image classifier that is able to differentiate between these three kinds of flowers. So before I show you a live demo of it, let me quickly tell you the intuition that's actually going under the hood. So on the left is the Inception model. As I said, it's trained on images from the ImageNet data set, and the gray box, or the white box, rather, these are the layers of the Inception model. And the final layer is the output layer. And in the output layer, you have one node for each of the categories that this model is designed to recognize. So for example, there's one node for Dalmatian, one for dishwasher, and so on. And the output of these nodes is the probability that this object is present in your given input image. So to reuse this Inception model, what I'm going to do is I'll just replace the final output layer with the new output layer, which is the categories that I want to, the categories that I care about, which is sunflower, tulip, and rose. And all I'm going to do is I'm going to reconnect the final layer just before the output layer to the new output layer. And these are the new these are the new model parameters that I'm going to train using my own custom training data set. Everything else in this white box, it's the same. I just reuse all the other model parameters. I just retrain the final layer model parameters. And so let's see a quick demo of this technique. So as I said, I collected some training data. I have images of roses, sunflowers, and tulips. And this is the retraining. This is the code, the TensorFlow code that I need to run. I won't run it here because it still takes like 5 minutes to train. So I've already trained a model, and I wrote some quick code that just takes this trained model and it does predictions on some test on any image. So I have a couple of test images which this model never saw during training. So I have an image of a tulip, and let's see. So as you can see, it's an image of a tulip, and let's see how the model predicts on this image. And you can see that the model is 99.98% sure that it's a tulip, and it's fairly certain it's not a rose or a sunflower. And next, I have an image that's slightly more complicated. It's an image containing sunflower and roses. So it's a bouquet of sunflower and roses, and let's see how the model does on this image. And again, you can see the model is 65% sure it's a sunflower, 32% sure it's a rose, and it's fairly certain it's not a tulip. So it's confused between sunflower and roses, and rightly so. So as you can see, I started with a very powerful inception model. I collected my own training data. I reused the inception model, trained the model for just 5 minutes, and I have a fairly accurate image classifier of my own. And as I said, so this is the link to the code lab if you're interested to create your own image classifiers. And as I said, you can once you train your model, you can deploy it anywhere. So you can even deploy it on mobile. If you go to tensorflow.org/mobile.html, you will find some samples of how you can do it on Android, iOS, and Raspberry. And this is an example of an app that was that uses an image classifier that was trained using the same technique. So it was trained to identify different paintings, and now it can identify different paintings in a museum. Okay, so let's come to our final approach to machine learning, which is to develop your own machine learning models for new problems. And of course, this involves a lot of research and experience to come up with really good models for different problems. And I don't claim to have any a uniform solution that just applies everywhere, or a quick hacky fix that just works everywhere. But what I can do is I can share some of the intuition that goes behind coming up with modeling techniques for new problems. And to make this conversation more productive, more effective, I'm going to so we're going to see how you can come up with machine learning model for a real life problem. So let's say I want to create an app. It's called Food.io. And the app, what it does is it predicts what the user wants to eat, right? So the user opens the app, yells something at it, say fried chicken. And what my app does is it suggests, say, top 5 food items that the user is most likely to click, right? And let's not care too much about what happens after the click. So say it's a single-click model where as soon as the user clicks a food item, it's just, the app knows the address and the restaurant and everything. It's just delivered automatically to your place. So let's see how you would go about, designing a machine learning model for this problem. So of course, so your input is the user query, and the model would predict top 5 food items. So you would have to start with some training data. So let's say you have very basic training data. You have pairs of queries and food items, and your metric of business interest is whether the user clicked it or not. So in your training data, you have the query, the food item that you showed for this particular query, and then the label is 1 if the user clicked on it, and it's 0 if the user did not click on it, right? So the simplest way to start, usually as in any other domain, is to start with a really simple model. And the really simple models in machine learning are the linear models. So what you can do is you can try to capture capture how the co-occurrence of a query and food item correlates with your label, right? So essentially what your model is trying to predict, it's trying to predict the probability of a click given a query and food item pair. So you can create a linear model like this where your inputs are these pairs of queries and items, and the model would learn which items work best for each query. So for example, this model might end up learning that for the query fried chicken, the item chicken and waffle has a higher probability of being clicked than the item chicken fried rice. So this is a very simple linear model that you can get started with, and of course, this model has certain limitations. So for example, this model has very specific set of items that it will predict for each query. So at some point, your users will grow tired of recommendations. So to generalize to newer items, now you can use some different techniques. So one of the techniques that you can use is actually try deep learning. And in deep learning, your aim is to learn the lower dimensional dense representations, also called embedding vectors, of these food items and queries in your embedding space. So you will, so all of your food items and your queries will be embedded into this embedding space, and there's a semantic relationship between the items in this embedding space. So two food items that are closer to each other are related to each other, and similarly, two queries, if they are closer to each other, they are related to each other. And during prediction time, you will for a given query, you will try to match items that are close to each other in this embedding space. So for example, you might in your training data set, the model might learn that the users who eat chicken and waffle, who click chicken and waffle, often also click burgers. So chicken and waffle and burgers will end up being very close to each other in the embedding space. And for the query fried chicken, this model would now not only just predict chicken and waffle, it will also recommend burgers. So of course, this is a way of generalizing to some new food item query pairs that you never saw in your training data. And of course, this model could also take it to the very extreme. It might try to generalize too well, and a lot of cases you have some very specific queries. So for example, if the user wants an iced decaf latte with non-fat milk, it does not make any sense to recommend, say, hot latte with whole milk, just because these two items are close to each other in the embedding space. So what you really want is a model that combines the power of both of these techniques. So it's able to memorize, or it is able to recommend very specific items for very specific queries, but at the same time, it is also able to generalize and recommend some new food items for these queries. And at Google, we call this wide and deep learning. We recently published a paper where we demonstrated that it works really well for recommendation problems. And if you want to learn more about wide and deep learning, you can go to this tutorial. It's TensorFlow.org tutorials wide and deep index.html. And this is the TensorFlow code. So we also open source the TensorFlow implementation of wide and deep. And this is the training code this is just 10 lines of code that you have to write to actually code the model that we just talked about in the last slide. So it creates a wide and deep model, and all you have to do is just specify what feature columns you want to use. You specify the architecture of your deep neural net, and that's it. Okay, so this is the last section of my talk. So right now, there are multiple solutions available for training your models, and for training your models. But TensorFlow, it's covered it's got you covered end to end. So once you have a trained model, your obvious next step is to serve it on live traffic, right? And TensorFlow has really simple, intuitive TensorFlow serving libraries, and you can bring up a server or service that uses these libraries and just point to the trained model, and it will take care of serving on live traffic. And it has some really nice optimizations, so even if the QPS to your service increases, it's able to scale really well by using techniques like batching and whatnot. So if you want to get started with TensorFlow and with machine learning in general, you can start today. There's a code lab session at 12:45. So in this code lab session, I'll try to introduce the basics of TensorFlow, and we'll try to. There will be plenty of opportunities to actually start coding using TensorFlow. And in general, if you want to know more about TensorFlow, know more about machine learning, you can go to tensorflow.org and you can go to tutorials. There are really good tutorials written by experts in their fields. They're not just code, like code snippets. They're actually explanation and intuition that goes behind these different machine learning techniques. And that's it. Questions?